This program will provide the basic understanding of absorption methods used in air pollution capture and various absorption control devices. We will cover what is absorption and what systems are considered absorbers, types of absorbers and their design and components, proper operating conditions, and causes of decreased performance, and performance monitoring. In absorption processes, gaseous contaminants are removed from a gas stream by transferring them to a liquid. That liquid is usually water or aqueous solution that contains chemicals selected to react with the absorbed contaminants. Absorbers can be designed to operate over a wide range of collection efficiency in order to meet specific emission limitations. Most systems operate with collection efficiencies of 70% to over 99%. The most important factor affecting collection efficiency is the solubility of the contaminant in the liquid. Solubility is a function of the temperature and pH of the liquid. Gases are more soluble in cold liquids than in hot liquids, and less soluble in liquids with low pH. System pressure can also affect solubility, but this is not a major variable in absorbers used for air pollution control, since they operate close to atmospheric pressure. The liquid's surface area and the time available for diffusion of the gaseous contaminants into the liquid are also important factors affecting performance. There are many equipment designs for contacting the liquid with a contaminated gas stream. The most common ones are spray towers, tray towers, packed beds, and spray dryers. Today we will be seeing all of these. The spray tower is the simplest device used for gas absorption. It consists of an open vessel with one or more sets of spray nozzles to distribute the scrubbing liquid. Typically, the gas stream enters at the bottom and passes upward through the sprays. This is referred to as counter-current operation. Spray towers can also be operated in cross-current or co-current arrangements. In cross-current absorbers, the gas flow is horizontal and the liquid sprays flow downward, while in co-current absorbers, the gas stream and liquid sprays both flow downward. Cross-current and co-current spray towers are not usually as efficient as counter-current units. The tray tower is a vertical column with one or more trays mounted horizontally inside. The simplest tray is a perforated plate that is referred to as a sieve tray. Other tray designs include impingement trays that have small impingement targets above each perforation to enhance gas-liquid contact, bubble cap trays that can operate over a wide range of gas and liquid flow rates without adversely affecting collection efficiency, and valve trays that have liftable valves or caps that improve gas-liquid contact when the gas flow rate varies. Regardless of the tray design, all of these units operate in a similar manner. The contaminated gas stream enters at the bottom and flows upward through the holes in the plates. The liquid enters at the top of the tower, flows across the tray, and then through a downcomer to the tray below until it reaches the bottom of the tower. The function of the trays is to disperse the liquid into droplets and the gas stream into bubbles, creating the gas-liquid surface area necessary for good absorption. Packed bed absorbers are the most common design used for gas collection. Packed columns spread the liquid over packing material in order to provide a large surface area for gas-liquid contact. There are many designs for the packing materials, but they all have large surface area while maintaining open areas for the gas flow. Although they are usually made of plastic, metal and ceramic packings are available when plastic cannot be used. Like spray towers, packed beds are classified according to the relative direction of the gas and liquid flows. The most efficient packed bed absorber is the counter-current design. The liquid is introduced at the top of the tower using sprays or weirs and flows downward over the packing material. The contaminated gas stream enters at the bottom of the tower and flows upward through the packing. In a cross-flow absorber, the gas stream flows horizontally through the packed bed while the liquid flows down through the packing material. In the co-current design, both the gas and liquid flow downward through the packing. This is the least efficient method of contact, and it is not commonly used. Spray dryer absorbers are used to remove acid gases such as SO2 and HCl from a gas stream. An alkaline solution or slurry is sprayed into the top of a large vessel through pneumatic or rotary atomizing nozzles. The gas stream enters at the top and middle of the vessel and is in contact with the droplets for 6 to 20 seconds. During this time, the acid gases are absorbed by the droplets and react with the alkali, while the heat of the gas stream dries the reaction products. The dry products from the spray dryer, along with any particles in the gas stream, are collected in a fabric filter or electrostatic precipitator. In all absorbers except spray dryers, the process of contacting the gas and liquid stream results in entrained droplets. Since these droplets contain the contaminants, they must be removed before the gas stream exits the unit. This is referred to as mist elimination or entrainment separation. The two most common mist eliminators are chevrons and mesh pads. Chevrons are simply zigzag baffles that cause the gas stream to turn several times as it passes through the mist eliminator. The liquid droplets are collected on the blades of the chevron and drained back into the absorber. Mesh pads are made from randomly interlaced fibers or woven fibers that serve as the collection targets. The density of the fibers controls the size of the droplets that can be removed. Where the source itself produces small contaminant droplets is in chrome plating. A very dense pad that can remove droplets a few microns in size is typically employed. To review, the common types of air pollution control absorption systems are spray towers, tray towers, and packed beds, all of which are followed by mist eliminators that remove final droplets. Another type of absorber, the spray dryer, uses fabric filters and electrostatic precipitators to remove particles. The control efficiency a device has in capturing contaminants is affected by temperature, pH, and the degree of gas-liquid contact. There are several operating problems that can occur in absorption systems. The most common of these include the following: inadequate liquid flow, low inlet liquid pH, poor gas-liquid contact, inadequate chemical feed rate, excessive liquid temperature, plugged beds or mist eliminators, and corrosion. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large systems are well instrumented. However, smaller systems may have limited instrumentation. Performance evaluation of these systems will be difficult unless measurements of important parameters are made. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced collection efficiency. The most direct indicator of system performance is the concentration of the contaminant in the outlet gas stream. However, since the gas stream is usually close to saturation at the outlet of the absorber, it is hard to extract a sample and remove the water without also removing some of the contaminant. And in situ analyzers have interference problems on gas streams with high moisture content. Also, commercially available monitors for many of the gaseous contaminants of interest can be expensive. Therefore, less direct indicators of performance are typically used. Perhaps the best indicator of adequate gas-liquid contact is the difference in temperature between the inlet and outlet of the absorber. If that temperature difference has decreased, it is likely that the collection efficiency has also gone down. The liquid flow rate into the absorber is also important. If the flow rate is being monitored, the value during the inspection should be compared to the baseline or permit value. A decrease in the liquid flow rate without a proportional decrease in the gas flow rate will usually cause a decrease in the collection efficiency. If the flow rate is not being monitored, other indicators can be used. Indirect indication of decreased liquid flow rate include a decrease in the pump discharge pressure or an increase in the pressure in headers supplying spray nozzles. Increased pressure in a supply header is usually due to plugging of the nozzles, which reduces the liquid flow rate. There are other parameters associated with the liquid that should be checked. High liquid temperature can reduce absorption efficiency for units in which the dissolved contaminant does not react with the solution. High liquid temperatures are not a significant problem for reactive type systems, since collection is not limited by liquid solubility. The pH of the inlet and outlet liquid should be evaluated. An inlet pH above 10 indicates a potential for scale accumulation that can plug nozzles, packed beds, and trays, reducing liquid flow rates and impairing gas-liquid contact. On acid gas scrubbers, an outlet pH below about 6 indicates that insufficient alkali is being provided to neutralize the acidic gases being absorbed, reducing the collection efficiency. Also, when the pH is below 6, severe corrosion of metallic components is possible. Increased pressure drop across the absorber may indicate plugging of trays or packed beds. A decrease in the pressure drop across a tray absorber may indicate warped or collapsed trays. Similarly, the pressure drop across the mist eliminator provides an excellent indicator of its physical condition. For mist eliminators that are used to remove the relatively large droplets created in the scrubber, the increased pressure drop usually results from a buildup of material on the mist eliminator surfaces, narrowing the openings for the gas to flow through. The resulting higher gas velocities can drag the collected liquid through the mist eliminator and back into the outlet gas stream, reducing collection efficiency. A decrease in the pressure drop across the mist eliminator may indicate structural failure. The performance of the mist eliminator can also be evaluated by observing the stack and areas adjacent to the stack. Rainout of droplets around the stack, mud lips, and discolored streaks at the stack discharge, or heavy drainage from open ports all indicate a poorly performing mist eliminator. Even though absorbers collect gases that cannot generally be seen, stack opacity is still a useful inspection parameter, although the presence of condensing moisture may make the observation difficult. Hydrochloric acid in most organic vapors can nucleate at high concentrations to form particles as the gas stream passes through the absorber. These particles are very small and are not efficiently collected. The presence of a visible plume usually indicates that the absorber is not functioning properly, since efficient absorption would reduce the concentration of the pollutants that can form particulate matter. Finally, component failure records should be evaluated. An increase from the normal failure rate indicates that the source should carefully evaluate the cause and correct the problem before equipment damage and excessive emissions occur. To review, to determine if an absorption system is working properly, field personnel should observe, if possible, the outlet gas stream contaminant measurement, but not likely available, the temperature difference between the gas inlet and outlet, the liquid flow rate and liquid pressures. Other parameters include liquid temperatures, pH levels, pressure drop, and stack opacity. As with any inspection of an air pollution control device, attention must be given to the system's records and physical condition and compliance with the applicable rules. Absorption systems used for air pollution control have many safety considerations, including corrosive liquids. Further training and experience will be necessary to complete all field tasks safely.